Hello. In the previous video, we studied different examples of limits. Today, we study how to evaluate limits analytically. So here is four sections in this video: properties of limits, limit of polynomials and fractional functions, limit of composite functions, and limit of tick functions. Let's consider properties of limits. Remember that in the previous section we studied limit of x cubed minus 1 over x minus 1 when x approaches 1. And we see that actually this is equal to limit of x minus 1 x squared plus x plus 1 over x minus 1 x approaches 1. And we simplify x minus 1. We got this is limit of x squared plus x plus 1 when x approaches 1, and we plug 1 into this function. We get 1 squared plus 1 plus 1, which is 3. That's what we learned from the previous video. The limit of this function is equal to 3, given that the function is not divided 1. Okay. Actually, we already applied some properties of limits in this case. What I can see right here is this. We have some polynomial in here, right? X squared plus x plus 1. And when I need to find a limit of this at x equal to 1, I just plug 1 into the function. Right? For this step, yes, everything is good. Because when I plug 1 into the function, I got some number, 3, a finite number. But in the previous step, right here, I plug x equal to 1 into the function, right? I got 1 cubed minus 1 over 1 minus 1, which is 0 over 0. Yeah, it's not a good one. So, we cannot do conclusion, right at this step. And that's why we need more. We need to factor the top, which is x cubed minus 1 equal to x minus 1 times x squared plus x plus 1. Because in this case, if you have 0, 0, that means 1 is the common 0. We already discussed about that. Okay, so what we can see in this, right? The first property is the limit of a constant c when x approaches some number a, that is just c. We already saw that when we study absolute of x over x. All right? We know that this function is not defined as 0 and does not have limit as 0. Why? Because when x less than 0, right? When x less than 0, the limit is negative 1. Negative 1 right here. I remember we use limit of absolute of x over x goes to 0 from the left, equal to the limit of negative x over x goes to 0 from the left. And this is nothing but limit of negative 1 when x goes to 0 from the left, and that is just negative 1. You see, in this case, c is negative 1. Okay, so if you have a constant, you can see a limit at any point, that is the constant itself. Second property, if you have some function in here, right? Let's say x, right? And x goes to a, that is just equal to a. Why? Let's draw it out. The function is y equal to x, right? So that is just straight line, y equal to x. Suppose this is a. Okay, so you consider the limit at a the function is defined at x equal to a, right? So when x approaches a from the left or from the right, you have this and then you have this, right? Or you can say, yeah, actually the function value is approached, a from the left and from the right. So the limit is equal to a. I just want to show you, on the graph. But actually, what we can see in this case, even you don't have x, even you have x to the n. So, parabola, some polynomial, right? X goes to a. That is just a to the n. Okay? Of course, in this case, I will say, yeah, n is bigger than 0. Because if n is less than 0, because when n is less than 0, we still have problem, right? So, when we discuss about such functions, and when we discuss about limits of such function at some point, the first thing we need to memorize is you just need to plug the point into the function. Okay, don't forget that. Just plug the point into the function. If you got a finite number, that is the limit. So this is your limit, okay? But if you get something strange, right? Do not get a finite number. So you need to do more in order to find the limit. That's it. That is my first principle when you need to find limits. Okay? Just plug the point into the function. Don't forget that. Let's go back to the previous example right here. I need to consider a limit at 1. I plug 1 into the function, I got 0, 0. It looks strange to me, so I need to do more, right? But when I consider this limit, I plug 1 into the function, I got 3. I'm done. 3 is the limit. Make sense? All right, let's consider more properties of limits before we go to examples. All right, suppose that you have limit of the function f of x as some point a equal to L, and the limit of g of x when x approaches a equal to k. Okay, then we have the limit of some number a f of x equal to some number c. Let's say that because we already have a. C f of x equal to cl when x approaches a. So that means when you multiply, the function with scalar, it's okay. It's nothing changed, right? You just need to multiply, the limit with the c in here. That's it. Okay. Or I can tell you, in this case, you can just bring c out of the limit. So you might think like, yeah, that is c limit of f of x. X approaches a. And since this is k, this is L, so you get CL, right? Second property, when you have limit of f of x plus or minus g of x, when x approaches a, this is nothing but the limit of f x approaches a plus or minus limit of g x approaches a. So say limit of difference or sum just equal to difference or sums of limits. I think that is very natural, right? Because when you have two functions, like you have sum of two functions, right? So you can break that out, right? Because limits is linear, so everything should be good. Okay, and the next property, we have product. You need to find product of f and g, right, at x equal to a. So this is just equal to product of two limits. So limit of f of x, x approaches to a, times limit of gx, x approaches to a. So we do not prove anything in this course. So, just accept that. All right. And the last property is the quotient. If you need to find limit of f of x over g of x when x approaches a. In this case, we suppose that the limit of g at a is different to 0. So in this case, we have limit of f, I write in short, over limit of g, right, equal to L. Of course, k is not 0, right, as we suppose. And if you have power, limit of f of x to the n when x approaches a, and suppose that in this case n is greater than 0, that is nothing but, L to the n. Those properties are very fundamental for limits. Don't forget that. And we use this all the time. Okay? But don't forget this principle, right? When you have a limit, just plug the point into the function. If you get a finite value, that is your limit. If not, you need to do something else. Example, you need to find the limit of 4x squared plus 5 when x approaches, for example, 2. You see, you plug 2 into the function, right? You get 4 times 2 squared plus 5. And that is what? 16 plus 5 is 21. This is already a finite number, right? Value. Done. This is your limit, and the limit is equal to 21. Okay? Of course, in this case, polynomial is very good one, right? Polynomial is defined everywhere. So for such function, you just need to plug the point, right, into the function, and you get what you need. All right? Let's consider another example. Limit of x squared plus x plus 2 over x plus 1 when x approaches 1. Look at this. We have fraction, right? But this fraction is different to the one we consider. You see that? For this function, when you plug x equal to 1 into this, you got 0 over 0. So that's why we need to do more, right? We need to factor the top and the bottom. But for this function, let's plug 1 into the function. You got 1 squared plus 1 plus 2 over 1 plus 1. You see, everything is good. So you get 4 over 2, which is 2. And the limit is 2. Done. You see, the reason of this is this function is defined at 1. The function is not defined at -1, but it is defined at 1. Agree? So what happened at -1? Let's do a more complicated one. X squared plus x plus 2 over x plus 1 when x approaches -1. Right? I plug -1 into the function. I just follow my principle, right? I got 1 squared plus 1 plus 2 over -1 plus 1, which is 4 over 0. So what to do in this situation? What to do in this situation? In this situation, we cannot apply this rule. We cannot apply this because k is 0. We suppose that k is not 0, but in this case, k is 0. So there's no way to apply that. So what is the conclusion? I tell you this. Undefined. No, we don't have this word in this course. No way. If you have a limit, you might have an answer like, yes, limit exists. Another one, the limit does not exist. We need to define everything in this. Maybe the limit exists, maybe not, right? Because we don't know. But it seems like the limit does not exist when you have this form. When you have a constant divided by 0, right? But it really depends. Look at this. In this situation, I need to consider two cases. The left limit, right? And the right limit. I hope you still remember this. Because when we consider a limit, right? In general, we need to consider left limit and right limit. So, what happened with the left and the right? With the left means x less than -1, right? Because you consider limit at -1. For the right limit, x greater than -1. Okay. I have the following one: x squared plus x plus 2 over x plus 1. On the top, when x approaches -1, I always have a positive number. Because when you plug, some point, right, which is very close to -1, this guy is always positive. Okay, so but the guy right here, x plus 1, is negative, and not only negative, it's very close to 0 and negative. Is that correct? So you divide some number which is positive, right? Divide by a number which is negative right here, but which is very close to 0. So it seems like the limit should be equal to negative infinity, right? And if you consider the right limit, you have x squared plus x plus 2 in here over x plus 1, right? The part on the top is bigger than 0 when x is close to -1, right? So you have some positive number divided by a positive number, and that number is very close to 0. So it seems like this approach positive infinity. Okay, so the left limit and the right limit in this case are not equal. So the function does not have limit. Okay, that is the one way how to consider this limit. There is another way. Okay, let me remind you about the function 1 over x. 1 over x right here. So I hope you still remember this, right? And we know that the limit of this function at 0 does not exist, because the left limit is negative infinity and the right limit is positive infinity, right? We discussed about this very carefully, and they are not equal, right? That's why the limit does not exist. So if you look at this function from the point of view of 1 over x, you see something very similar. What is similar? On the top you have x squared plus x plus 2, but at -1, right? At -1, x squared plus x plus 2 is just 2. How about that? Let me write it down, okay? At x equal to -1, x squared plus x plus 2 is -1 squared minus 1 plus 2, which is 2. So you see something like, yeah, in that case, 2 over x plus 1, right? But at x equal to negative 1. So if you have 2 over x at x equal to 0, they are very similar. You see that? So, the coefficient 2 here does not affect on the existence of the limit, right? So this function does not have limit at 0. And this function, of course, does not have limit at negative 1. That's it. In general, we may consider like this: 2 over x plus a at x equal to negative a. And this function does not have limit at x equal to negative a. Okay, don't forget about that. I think I told you that, we need to pay attention on this function because this is very, very typical limit, 1 over x. All right? Let's move to the next example. Now we have some composite function. F g of x. Okay? So let's say this is h of x. And the limit of g of x at x equal to a is L. At the same time, the limit of f of x when x approaches L equal to f of L. Look at this. We have the limit of g is L, but we consider limit of f at L because the function f, of g of x, because we have composite function in this case, right? So, if that happens, then, the limit of f when x approaches L is just f of L. Agree? Again, right? Just look back the principle I just told you. When you see a limit right here, you just need to plug the point, right, into the function. If you have finite number, perfect, right? So in this situation, the limit of f of g of x, but at a, okay, at a, is just equal to f of L. So that is, good property for composite function. Okay, so let's consider the following example. Let's say the limit of square root of x squared plus 4 when x approaches 1. I plug 1 into the function. Even here we have a composite function, but I just plug 1. I got square root of 1 squared plus 4. I have square root of 5. It is a finite number. I'm good. Okay? Of course, you have two functions in here, right? If you want to apply, the property for a composite function, you might think like, yeah, we have square root as one function. Another one is x squared plus 4. And then when you plug x equal to 1 into x squared plus 4, you got 1 squared plus 4, which is 5. And then you plug 5 into the square root, you got the square root of 5. You see? It's almost the same, but when you have a function, you need to consider the limit of that function at some point. Just plug the point into the function. Okay? Another example, you consider limit of cube root 2x squared minus, okay, let's say minus 10 when x approaches 3. Let's say, what happened if we plug 3 into the function, right? I got cube root of 3 squared minus 10. So this is what? Cube root of, that is 9. His 2 is 18. 18 minus 10 is 8, right? Cube root of 8, which is 2. It is a finite number, which is good. So I just copy everything in here, right? So I have cube root of 3 squared minus 10, which is cube root of 8, which is 2. That is my answer. All right. In order to finish this video, let's consider some examples of limits of trig functions. I remember when I taught pre-calculus trig functions, I think it is very interesting in the sense that it's difficult if you want to teach this difficultly, but it is easy if you want to teach it easily. So it really depends, okay? So limit of trig functions is almost the same, right? So when we're talking about trig functions, I always try to remind you and to teach you to understand the unit circles, because that is really important to understand and to find limits of trig functions. Okay, so let's consider unit circle right here. I tell you, right, my unit circle is a little bit different than the unit circle you learn from high school. So this is 1, this is -1, this is -1, this is 1, right? I want to use the unit circle to study trig functions. Okay, so let's say if I have a point right here, this is the angle x, right? So in order to find the cosine, I just take orthogonal projection, right, of this point onto, let's say, the x-axis, right? So I have cosine of x in here, and the y-axis will be the sine values, right, of the angle x. Make sense? And if you want to see the tangent, this is your tangent. That is your tangent axis. So I can write this is the cosine axis, this is the sine axis, this is the tangent axis, and at the same time we have cotangent axis, which is like this. This is cotangent axis. Okay, so if you have an x right here, okay, you want to find cosine, you just take this. You want to find sine, you take this. If you want to find tangent, pretty easy. You just connect that point with the origin, okay, and that will intersect with tangent right here. So that is your tangent x, and the origin of tangent is right here. Don't forget this. This is 0 for tangent, okay? This is 0 for tangent. This is 0 for cosine and sine, but the 0 for tangent is right here. And the 0 for cotangent is right here, okay? So if you just connect this, extend this to this line, that will intersect with cotangent, and that is the cotangent value of the x. Okay, so I hope that, you understand the picture right here. So each time when you have an x, you can find cosine of x, you can find sine of x, you can find tangent of x, you can find cotangent of x. That is my unit circle. Okay, and on this unit circle you have different values. Let's say this is 0 for the x. So x will start from here, right? X go along, go along the circle. So this start from the 0. The angle is just 0. And then go to this point, you have pi over 2, right? That is pi over 2. And then move to this point, you have pi or 180 degrees, right? You move to this guy, you get 3 pi over 2. And you go back to this point. So that is 0, but at the same time, that is 2 pi, right? They just share the same position on the unit circle, right? And then whatever you want, right? You can go more different routes on the unit circle. So, it's very interesting. Okay, now that is about the unit circle. Let me consider some example in here. I want to consider the limit of tangent. When x approaches 0. Okay, So I want to use the unit circle. Look at this. Let me draw another one, right? Each time. I know the tangent is right here. That is my tangent. Okay. X approaches 0. 0 is right here. X approaches 0 from the left or from the right, right? So you may, yeah, from this and from this. Don't forget this. X in this case, the angle. So, you know, X just move along the circle. Don't forget that, okay? So what happened? If X approaches to this, right? Let's say this is your X, okay? So I want to find a tangent of X. So this is tangent of X. We just talked about this recently. When X approaches 0 on the unit circle, so this point approach to 0, right? So the right limit is equal to 0. And if you want to consider the left limit, you do almost the same thing. This is your X, you connect with the origin, this intersect with the tangent A6 at some point, and that is the tangent value when X is less than 0, right? And when X approaches 0 on the unit circle, your point right here also approaches 0. So that means the left limit and the right limit are equal. And the tangent is equal to 0. And X equal to 0. Alright? You know, you may write, yeah, tangent is sine X over cosine X when X approaches 0. And when you plug 0 into this function, you got sine of 0 over cosine of 0. And that is 0 over 1, which is 0. A finite number, you are good. But I really hope that you understand, you know, how to explain this using the unit circle. I tell you, this is complicated because some of you might not study at the high school, okay? But we really need this when you study limit of trig functions. All right, let's consider another example. Limit of x psi of x when x approaches 0. Again, I just plug the point right into the function. So let me see, what is that? 0 psi of 0, which is 0. I'm good. So the limit is equal to 0 psi of 0, and that is 0. So everything is good, right? But look at this example. Limit of psi of 1 over x when x approaches 0. Exist or does not exist? How do you think about that? I tell you, this does not exist. And why? Okay, so I would leave this example for you. If you have an answer or explanation, please feel free to let me know. I think we can finish this video right here. In the next video, we will study the strategy of finding limits, and I think we have more interesting stuff in the next video. Thank you for watching.